So thank you very much for Professor Fu's introduction. So I'm the last one. I will try to finish in 20 minutes, same as Jinzhou. Okay. So today my topic is slightly different. It's about calcium rechargeable batteries. Well, in fact, everyone's pocket have a battery which powering your cell phone. It's a lithium-ion battery. So when I'm going to talk about calcium battery, something different. So today's story is like that. So why I'm working on calcium battery. So how to do calcium battery and what is the next? The calcium battery is a very new topic and very few people work on that. So first, let's go to why you're going to work on calcium battery. That is a big background that the energy usage in our world, 80% of them coming from the fossil fuel, which lead to the global warming and the climate crisis. So now we are trying to use the sustainable energy, which is intermittent, and we need to store them in the batteries for the portable electronic devices or e-transportations, which is green, considered green, at least for the customers. Of course, we can also store them in the energy storage techniques for backup usage or some other applications. So today, as I just said, that most of the batteries are lithium-ion battery in the market, which are powering your cell phone and other laptops, electronics, and so on. And the lithium battery mainly use the lithium-ion as a charge carrier. And in the near future, lithium-ion battery, the market will explode dramatically. So when we look at lithium, the storage in the Earth's crust, we find that the lithium is not something rich. The storage in the Earth's crust is only 22 ppm. So it's something expensive, just like gold. So currently we also say the light gold, I mean the lithium. So in the future, if you want to use lithium in large scale, we need to find new elements, which is rich. So here, calcium, you can say that it's more than 3,000 times richer than lithium. So if we want to use calcium as a charge carrier in your new battery systems, the key question come to our mind is that you need to find suitable electrode materials, like in your battery, negative electrode and positive electrode. So well, here we look at the battery chemistry. In fact, for the battery chemistry here, we can divide them into monovalent, divalent systems. And the most popular system is lithium. At first, you can say it's for the divalent system, like magnesium, calcium, and zinc, they can transfer 2 electrons per charge carrier, means they have a higher energy density. That means we have a smaller battery, but have which is more powerful. Another benefit is coming from the storage abundance of calcium, which is more than 1,000 times richer than lithium. Here, lithium is only 18. Another reason to work on calcium is that calcium is so hard to do, and few people work on that. So here I list the breakthrough works reported for other battery system, like a magnesium battery, zinc battery, aluminum battery. All the breakthrough has been reported in big papers like Nature. Well, why people don't work on calcium? Because it's too hard. So I will work on this hard topic. I'm in my group. So if we want to, the next question is how to work on calcium battery. For any battery, you need, the first question you need to answer is to find the suitable electrode materials. I mean, for stable electrode materials, it contains anode material and cathode material. For anode material, our first choice should be graphite, because graphite is the commercial, is a commercial anode material in lithium-ion. So if we can successfully use graphite in the calcium, we can directly use the industrial chain in the market to prepare new battery systems. But unluckily, it is not straightforward to store calcium in the graphite. You can say that I find 2 papers in the old time, which just insert calcium into graphite, but not in a reversible way. So can we insert calcium into graphite in reversible method to enable it as a battery? We screen lots of electrolyte and find that, yes, we can do it. For the first time, to insert graphite, calcium into graphite reversibly in this method. And the cyclic stability is good, can go to 200. Recapability is super good. We can cycle at 2 ampere per gram. That means we can cycle 10 minutes of the battery. So it's very, very good. And I think this breakthrough for this work that is we insert calcium in graphite for the first time, which opened a new avenue towards the commercialization of graphite-based calcium battery. So next question is, how calcium intercalates in graphite? So we conduct a synchrotron in situ XRD. Here I will not explain too much. I think it is a little new, something new to you. So anyway, from the in situ XRD, we can see the reversible curve change. That means the phase evolution, which is reversible from the insertion and extraction. And by calculating the the position of caching into the graphite, we can estimate that the caching intercalation is the staging process from stage 4, stage 3, and stage 2. So you can see the blue points refers to caching ion. They are slowly integrated into graphite layer by layer. So graphite is a layered structure. So this slide shows you how the caching ion integrated in graphite. So next is where the caching integrated graphite. So we conducted the NMR characterizations. We can show that the caching ion, after the caching integrated graphite, the carbon spectra slightly shift. That means the diamine solvent also integrated in graphite. By measure the weight change and calculations, we can determine the final configuration of the graphite intercalated, just like this, that caching ion integrated into graphite together with the solvent. This is a new finding in this field for the fast charging caching batteries. Well, next we move our views to organic electromaterials, because compared to organic materials can be greener because we can directly obtain them from nature. But organic materials suffer challenges of dissolution or sacrifice of the capacities if you polymerize the organic materials. So my students find that if we use PDCDI is kind of a very widely obtained dye material, so you can buy it from the market directly, very cheap. Okay, so these are the characterization of this material, XRD and SEM. You can see these are the as received material. We don't treat it anymore, and the carbonyl groups in this function are possible to allow the storage of caching ion. Luckily, when we test the material caching battery systems, we find that, okay, so good. The large amount of caching ion can be stored in the graphite with extremely long cycle stability, say thousands of cycles. In real batteries, that means 3 years, okay? So, and we can also go 5 ampere per gram. That means we can cycle the battery in 10 minutes. So it's very, very fast. So why it's so good? First, we need to understand where the caching is stored. So by FTIR and XPS, we found that the caching ion are stored in the carbonyl groups. And by in situ RIAM and XRD, we see there is no peak shift of the carbon layer. So that means there may be no insertion of the caching ion between the carbon layers. So I mean, the caching ion will not go in here because this place is very small and it will be very slow for caching to diffuse through. Through the EQCM and DFT calculations, we can determine that the caching ion may go to the 0 to 0 directions. It's a fast diffusion path. So that is why we can obtain the fast charging anode materials. So after obtaining the anode, next we go to the cathode. I mentioned that both anode cathode are important for the new battery systems. For cathode material, because caching is very larger than lithium-ion, so it may induce the slow diffusion of the caching ion and the large volume expansion of the cathode materials. So it's very hard to find a new host that allowing the rapid and stable caching storage. So here we found that in the NVPF, which is a Nasicon material in the sodium battery, can be used to store the caching ion with a high capacity of around 90 milliamp per gram and super stable capability, say 500 cycles. This is the best that's reported for caching batteries. That is why in this paper, after we submit, is directly accepted by Nature Communications without further comments. So it's a breakthrough. And now, why it is so stable? We conducted the in situ XRD and calculated lattice parameter change. We found that the lattice parameter, I mean the structure change in the top up, the structure change is very, very small. It's only 1.4%. So such a low volume change during the insertion and extraction of ion can maintain the host stability. And next is why so fast. We conducted the GITT to measure the diffusion coefficient. It's in order of 10⁻10 to 10⁻11. It's comparable to the commercial cathode materials in the lithium-ion battery. So it is very, very good. And we also trying to understand where the calcium ion inserted. And we found that by the calculation, we found that calcium ion are most of them are inserted in the vacancy where we create by extract the sodium ion. Well, normally we say seeing is believing, or in Chinese we say 眼见为实. So we also conducted the CS STEM. So by the high resolution GM, you can directly observe where the calcium items are inserted in the host. So overall, this is a stable host for cathode material, and it can allow the high voltage. So we further improve the voltage of the working electrode by induce more fluoride in this structure by some manufacturing process to improve the voltage, because for cathode material, the voltage is very important, which will determine the energy density of a battery. So finally, we have anode cathode. So we combine them together. So we combine the graphites and MVPF calcium full cell. We also established calcium metal and MVPF full cell, which is for the first time which delivers energy density of 400 volt over per kilogram, which is comparable and higher than the lithium-ion batteries. But calcium ion battery, so what is the next step? The calcium battery is a very new field, and we just conduct some primary research on the anode material, cathode material, use commercial materials, say graphite and MVPF, which are commercial materials. In the future, there is still a large area for us to explore, and it's a very promising field. I think that is why RIAM invests 2 projects still working on this. Yes, so that's all. Thank you. Thank you very much for your attention.